Test of uniform convergence of the series sigma x upon n raised to power p plus n raised to power q into x square, where x belongs to closed interval ab when 1 p is greater than 1 and q is greater than equal to 0. Second, 0 is less than p is less than equal to 1 and p plus q is greater than 2. Now solution 1, when p is greater than 1 and q is greater than equals to 0, here f and x equals to x upon n raised to power p plus n raised to power q into x square. Since x square is greater than equal to 0 for all values of x belongs to closed interval ab, so n raised to power q into x square is greater than equal to 0, which implies n raised to power p plus n raised to power q into x square is greater than equal to n raised to power p, which implies 1 upon n raised to power p plus n raised to power q into x square is less than equal to of 1 upon n raised to power p, which implies x upon n raised to power p plus n raised to power q into x square is less than equal to x upon n raised to power p. So modulus of f and x equals to modulus x upon n raised to power p plus n raised to power q into x square is less than equal to of alpha upon n raised to power p equals to mn for all values of x belongs to closed interval a b, where alpha is greater than equal to a maximum of modulus alpha, modulus a and modulus b. Since sigma n varies from 1 to infinity, mn equals to sigma n varies from 1 to infinity alpha upon n raised to power p is convergent for p is greater than 1. Therefore, by the Weierstrass M test, the given series is uniformly convergent for all the x belongs to closed interval ab and p is greater than 1. Second, when 0 is less than p is less than equal to 1, p plus q is greater than 2. Since f and x equals to x upon n raised to power p plus n raised to power q into x square, so d over differentiation of f and x with respect to x equals to applying the product rule n raised to power p plus n raised to power q into x square as it is into differentiation of x is 1 minus x as it is differentiation of this term. Here the first part is constant and second is n raised to power q into x square differentiation is 2x upon n raised to a p plus n raised to a q into x square denominator square, so equals to n raised to a p minus n raised to a q into x square upon n raised to a p plus n raised to a q into x square whole square. For the maximum and minimum d f n x upon dx equals to 0, which implies n raised to power p minus n raised to power q into x square equals to 0, which implies n raised to power p equals to n raised to power q into x square, which implies x square equals to n raised to power p upon n raised to power q equals to n raised to power p minus q, which implies x equals to n raised to power p minus q upon 2. Also, again differentiation of f and with respect to x, so d square f and x upon dx square equals to n raised to power p plus n raised to power q into x square as it is differentiation of second terms is 2 minus 2 n raised to power qx minus n raised to power p minus n raised to power q into x square as it is, and differentiation of second terms n raised to power p plus n raised to power q into x square into, again this is containing the term of x, so 2 into n raised to power q into x upon n raised to power p plus n raised to power q into x square whole raised to power 4 equals to minus 2 n raised to power qx n raised to power p plus n raised to power q into x square into n raised to power p into n raised to power q into x square plus 2 into n raised to power p minus n raised to power q into x square upon n raised to power p plus n raised to power q into x square whole raised to power 4. So from this term is 1 power of this one cancel out, so minus equals to minus 2 n raised to power q into x n raised to power p plus n raised to power q into x square plus n raised to power p minus n raised to power q into x square upon n raised to power p plus n raised to power q into x square whole raised to power 3. So n raised to power p is the 3n raised to power p and nq is this plus n 2 term of n raised to power q into x square. So this is minus n raised to power q into x square, so equals to minus 2 n q raised to power n raised to power q into x into 3 raised to power 3 into n raised to power p minus n raised to power q into x square upon n raised to power p plus n raised to power q into x square whole raised to power 3. Now d square fn x upon dx square when x value is n raised to power p minus q upon 2, substituting the value in this term, so 2 n raised to power q into n raised to power p minus q upon 2 minus 3 n raised to power p minus n raised to power q into n raised to power p minus q upon n raised to power p plus n raised to power q into n raised to power p minus q whole raised to power 3 equals to minus 2 n raised to power q into n raised to power p minus q upon 2 into 3 raised to power 3n raised to power p minus n raised to power p upon n raised to power p plus n raised to power p whole raised to power 3, so equals to minus 2 n raised to power p plus q upon 2 into 2 n raised to power p upon 2 n raised to power p whole raised to power 3, so equals to minus 2 n p plus q upon 2. So from this 1 power of this term is cancel out, so it remains power 2, so minus 2 n p plus q upon 2 n raised to power p whole raised to power 2 equals to minus 2 n p plus q upon 2 4 n square into p 4n raised to power 2 into p equals to minus 1 upon 2 n raised to power p plus q upon 2 minus 2 raised to power p equals to minus 1 upon 2 n raised to power q minus 3 raised to power p upon 2 is less than 0, which shows that the fnx is a maximum at x equals to n raised to power p minus q upon 2, and the maximum value of the fnx is n raised to power p minus q upon 2 upon n raised to power p plus n raised to power p equals to 1 upon 2 into n raised to power p plus q upon 2, which implies modulus fnx equals to modulus x upon n raised to power p plus n raised to power q into x square is less than equal to of 1 upon 2 n raised to power p plus q upon 2 is less than 1 upon n raised to power p plus q upon 2 equals to mn. Since mn sigma mn is equal to sigma 1 upon n raised to power p plus q upon 2 is a convergent if p plus q upon 2 is greater than 1, and that is the p plus q is greater than 2. Therefore, by the Weierstrass M test, the given series is convergent for all values of x belongs to closed interval if p plus q is greater than